let's talk about recursion. What is recursion? And we can say that recursion is defined by recursion and so on. So basically, it's a thing which is defined by itself. And what it means is that if you want to define something, we can use the definition of this thing itself, or in programming, to find a solution for a problem, we kind of use the same solution. Or in other terms, we can say that the function calls out itself. Let's see some examples and how it works. So, and before we go on, I can show you that if you search recursion in Google, you can see that it points to this did you mean recursion again. So if you click on that, you get on the same page. So Google does the same thing as I did in my first slide. So it defines the recursion as recursion. Let's see an example. So let's say we have a problem. We want to empty a vase with 5 flowers in it. And how we would approach this problem. So first, what we want to do, we want to make sure that the vase is not empty. And if it's not, then we take out 1 flower. And now we want to empty it with 4 flowers. And again, if it's not empty, we take 1 flower, and we have the same problem with 3 flowers, and so on. After a few steps, we reach to the stage where we have 1 flower. We take this 1 flower out, and we want to empty the vase with 0 flowers. And now we can say that the vase is empty and we have solved our problem. So if you want to generalize our problem, we can say that we have a problem where we want to take n flowers out of the vase. And the steps to kind of solve this problem, first we take 1 flower out if it's not empty. And then we call out the same problem with n minus 1 flowers. So basically, if we start with 5 flowers, then we call out or basically solve the same problem with n minus 1 flowers. And here is the code. So we have a function, empty vase, and it has a parameter flowers count. And what we do inside that? First thing is that if the vase is empty or if there are no flowers inside it, then we say it's done. And in other case, if there are some flowers in the vase, we call out the same function, but we pass in the value of the flowers minus 1. So let's try to run this code. So here is the same code. And now if I want to execute it, I just add main section here, and let's call out the empty vase, and with 3, for example. Now if I run the code, I can see it's done at some point. But currently I don't see any steps. I would like to see what's done during the execution of my code. So first thing would be I will print out my flowers count. So every time this function is called, it prints out how many flowers are there in the vase. And as you can see here, we have 3, 2, 1, 0, and then it's done. And now what is important is that we have to have this else part here. If we would have the code as that, so we don't have this else part, and we call out this empty vase. And if I run the code, you can see I got an error, but what happens is that it actually reaches below 0. So it doesn't matter whether I emptied it or not, it still calls out the same function. So that's why we have to make sure that this recursive callout is terminated at some point. And usually my termination condition is here, but the problem is that if I don't have this else part, then this part of the code is always executed. So that's why I have the else part here. So this part is only executed if this flower count is above 0. if I have something to take out. Now I see that my program works. I get all the flowers out of my vase. Okay, let's do another example, counting. And the problem is how many people are in a queue. So I have a list of people. I want to know how many people are there in this list. And how we could approach this problem. So let's say we have some people here. Let's draw 5. Although my example has 3 because it takes less space. But I have 5 people. So how can we solve this problem? Of course, we know that we have, for example, function len in Python. We can also iterate over this list. But let's try to solve it recursively. And how we solve problems recursively. So basically, we usually divide the problem into smaller parts, and then we solve the smaller part. But because of having solved this smaller part, we can actually solve the whole exercise. And here we do it like that. Let's say there are people in this queue, and I ask from the first person, how many people are there in the queue? And how you can do it, the first solution would be that you go over and count all the people. But another approach is that you solve it like that. You say that, okay, including me, there is 1 plus all the people here. But I don't know how many people there are. I'm too lazy to go and count. I ask from my neighbor or the next person next to me. So I ask from him or her how many people are in a queue, including you. So this person also says that it's 1 plus and everything after me, or every person after me, and so on. So basically, everyone says that there is 1 plus, 1 plus, 1 plus, but the last guy knows that there's nothing after me, so I can say that this is the first guy who can actually say that there is 1 person in a queue. And now he or she can pass it on here. Now this person here knows that together we have 2 people in this queue, and he or she can pass it on here. And now we know that this guy can say that including me, there are 1 plus 2 equals 3 people in a queue. And again, this one is passed here. This person here knows that there are 4 people, including the same person, and then now we can say that 1 plus 4 equals 5. So that's a recursive solution to this problem. The first person knows that there is me, or 1, plus the rest of the queue, or rest of the length of the queue. And you answer the question. I cannot answer right away. I had to ask from my neighbor. He or she also wasn't able to answer right away, so those people were waiting until it basically went all the way to the end, and now it came back, and the first person was able to say that there is 1 plus 4 people in a queue. And basically that's the same as I draw here. The second person says that 1 plus the rest of the queue, and the third person says the same, and so on. But after the third person, there are no more people in my example. So this person can say that altogether there is 1 person in the queue. And then the second person can take the answer from the third person, which was 1, and add it to him or herself. So altogether there are 2 people in a queue, and the first person takes this 2, adds it to him or herself, and gets 3. So let's try to generalize again. So we want to count a people in a queue. If the queue is empty, then we return 0. That's the base case, or we always have to have this termination case. So if the queue is empty, then we return null, or 0, there's no one to ask how many people there are. Otherwise, the result is 1 plus the count of the people in the rest of the queue. So here is also an example. So we have a function, count elements, and we have a list of elements. So instead of using len, we are len directly, we are using recursive solution here. Although this solution actually uses len itself. So if the len of this list is 0, then we return 0, because if it's an empty list, then there is nothing to do. Otherwise, we return 1 plus count of elements. We call out the same function, but we pass on the smaller q. So basically this is a slice which takes, it basically divides this from here. So this is 1 plus, and we want to know what's the result of the function using the smaller q, where the first person is removed. And same applies actually here. So here we take 1 plus and the length of the rest of the queue. So here I could actually write function. So this is 1 plus function where I pass in the 4 elements and so on. Let's have another example. We want to count how many A's are there in the text. So it's pretty similar to that one, but here we counted everyone. But in this example, we only count if the value of the symbol is A. So it's a bit different from that. So again, let's divide the problem into smaller problems. And what we can do, we can check the first symbol, as we did here. In this example, we just took the first person and counted it. But here we take the first symbol and check whether it's A or not. So if it is an A, then we can say that there is 1 A. And otherwise there are 0 A's. So basically, yeah, if I take an example, I probably have it on my slides, we can go through that example. And to solve the whole problem, we solve it for the first symbol. So whether the first symbol is A or is not A, here I always add 1. But depending on the first symbol, I can say whether I add 0 or 1. And then we add the rest of the text, or the solution for the rest of the text. And we have to have a base case, so that's the condition where the recursion is terminated. And the base case can be if if the string is empty. So if the string is empty, there are certainly 0 A's. So let's take an example, A, B, C, A. And what we do here. So as I said, we want to divide it into smaller problems. And first we see this first part, or the first symbol basically. And the first symbol, because it is an A, we can say that the solution for this whole problem is that I take the first symbol and I can say that the first symbol is A, and I call out the same function with the rest of the string. And if I'm solving this problem, I can think, or I can see this f function here as the correct solution. So if I know that there is a correct solution which can count the A's, or actually solve the problem, whatever problem we have, I know that this one works for the rest of the input and this one is done for the first part. So if I know that this somehow magically returns, I don't know, 7, which is correct, then I only have to worry about the first symbol. And the first symbol, as I said, because it's an A, we say that this is 1. There is 1 A plus everything I can find from this part. And to calculate, or if the Python to be able to calculate this, it has to know the result. So now the Python starts working with that function. And again, to solve this problem, we take the first part. Sorry. So basically we take between the B and C. Let's have this C here. And now, because the first symbol is not A, I can say that it's 0 plus function of C and A. Because let's forget that we are using or calculating the previous example. Let's see this as a separate task. So if there is a function which has to calculate the count of A's from BCA, then it works as that. It takes, because the first symbol is B, there is 0 A's, and now I want to get the result from the rest of the string. And again, let's do the same. So here we also divide it from here. We say that it's 0 plus function from A. And again, we can say that this is a separate function. We don't care that there was someone who called us. And here we say that function from A is 1 plus function from empty string. Again, this can be seen as a separate callout. And we say that if we take empty string, we can say that it's a 0. So this is the base case. That's always something you have to come up with yourself. Otherwise, you just generalize or try to find a kind of smaller steps how to solve this problem. But the base case is something you have to come up with yourself depending on the problem. So often it's, if we are dealing with string or a list, then normal case is that we take steps by taking the first element of this sequence, and the end condition or this base case is when the input sequence is empty. But there are, of course, other ways. For example, if you try to, I don't know, increase something, then the base case can be different. Okay, but here we can say that this function from empty string is 0, and now I know that this function from A is actually 1. 1 plus 0. And here, again, now we know that the function from A is 1. Function from CA is 0 plus function of A is 0 plus 1 is 1. Here the same. A function from BCA is 0 plus function from CA, but function from CA gave us 1, and now we know that, again, this is 1. And now if I want to calculate this, I get the result of 2. So basically here is the same thing I did. So first I go deeper into this base case, and then I come back to actually calculate the result of the original or the first input. And here is an example. I will just try to execute it in PyCharm also. So I take the same example, A, B, C, A, and let's see what happens here. So first let's see the code here. So I get this string as text variable. If the length is 0, then I return 0. This is like the base case. There is no point to go on if the input is empty. I will just add a line break here. Empty line, it's easier to read. Then we do some splitting. Basically, first we take the first character. This is the part what I'm trying to solve first. So I take the first symbol, and then I take the rest of the text. So rest of the text is basically slice starting from the second symbol. So this is splitting. Basically, we divide this string into 2, as I've split it here with my different color line. And here I calculate the result for the first symbol. So the default value for the first char is 0, and if it is A, if the first symbol is A, then I say that the first char result is 1. It could be written also so that if the first char is A, then I put 1 there and else put 0 there. So it's matter of the coding style. So here I just probably kind of was able to skip one else line. But basically the idea is to calculate the value for this first number, whether it's 0 or 1. And now I return, basically we can see this line here. So I return, basically we can say that there is return here. So it returns the value of the first symbol, which is either 0 or 1, and it returns the result of this same function, but called out with the rest of the string. So that's the case here. So count A is the function, and the rest of the text is whatever remains after I remove the first symbol. So if I execute this code, I can see that it counts all the A's and it gives me 2. The same code can be written with 2 lines, basically. The code or the idea is basically the same, but I just don't use the variables here. So the first condition is still the same. If the length is 0, then return 0. And here I just don't declare variables. I just basically use this return sentence here. And for this first char result, I use inline if condition, basically. So it's 1 if the text at position 0 is A, otherwise it's 0. So this is the first part. And then I call out the same function with the rest of the string. Again, instead of using this variable, I just use this same slicing here. And often the solutions to recursive programs are 2 lines of code, basically. The one is the base case, the other is the call out for the next step. But of course, depending on the solution, it can be more complicated and so on. But the idea is still the same. Usually you have the base case and then the solution to this first or this concrete step. So let's try to sum up a bit what we have done so far. So recursion is a solution or a program where the function calls itself. So as we saw here, we have a function which calls itself to solve the problem. A function has to have a base case, so basically it's a termination condition. At what point there is no looping or no call to itself, because otherwise if I have a function which calls itself, for example function f, and here I do something and I call out this same function. So what happens is that it's endless recursion, so I end up calling the same function over and over again. And usually we try to divide the problem into smaller sub-problems. So as I saw here, instead of trying to solve the whole string at once, I solve the problem for one symbol and the rest comes out of that. And every recursive solution can be written iteratively. Iterative solution is a one where we use looping or while or for loop and vice versa. So if I have a regular solution to a problem where I use for loop, I can write it as a recursive program also. Let's see another example, Factorial. This is pretty typical example for recursive solutions or problems. So Factorial is actually defined. It's a mathematical function which is defined basically using recursion. So and it's written as that. So this recursion or the factorial itself is n and exclamation mark. It is equal to 1 if the n is 0, and if the n is larger than 0, then we say that it's a recursion or factorial of n minus 1 multiplied by n. So basically it's recursion written in to this definition already. So basically it's a product of all positive integers less or equal to n. So if I have, let's say, 3 factorial, it's basically 3 multiplied by 2 multiplied by 1. It doesn't matter what's the order, whether you start from 1 and end up with 3 or vice versa. So mathematically it doesn't matter. It might be, it might depend on your, I don't know, solution, how you solve this problem. But by the definition, we actually have to solve it so that we, at least as written in my slide, I first should actually calculate this one for n minus 1. So basically this one is a bit more accurate. But let's see an example. So I have 4 factorial, and what's the result of that? So first, if I take the definition, it is n minus 1 factorial multiplied by 4. So it's 3 factorial multiplied by 4. Now, in order to calculate what's the factorial of 3, I have to calculate 2 factorial multiplied by 3. So let's write it here also. So if I have 4 factorial, by definition it's 3 factorial, I give some space here, multiplied by 4. This is n minus 1, and n again. This is basically the same as, now I have to calculate what's 3 factorial. 3 factorial is 2 factorial multiplied by 3. And this 4 still remains here. So now I basically replaced this one. Again, to calculate it, we have to know what's the 2 factorial. 2 factorial is 1 factorial multiplied by 2, multiplied by 3, multiplied by 4. So now I calculated this 2 factorial. And by the definition, 1 factorial is 0 factorial multiplied by 1 and multiplied by the rest of the elements. And by definition, the 0 factorial is 1. So basically I should write 1 here. And now I can calculate the end result. So basically it's 1 times 1 times 2 times 3 times 4, and it should be 24. So that's how we calculate the factorial. Another example, which is basically defined by recursion, is Fibonacci sequence. And the sequence is defined as follows. So basically the first 2 elements are 1. And besides that, the element at position n is defined as a sum of 2 previous elements. So to calculate f at position 3, I take the Fibonacci at position 2 and plus Fibonacci at position 1. Because 2 and 1 are both 1, then I can say that Fibonacci at position 3, or the third Fibonacci number, is 1 plus 1 is 2, yes. And here are the sum of the numbers. So basically, every time I want to calculate a result, I take the 2 previous numbers and add those up. So to get 2, I take 1 plus 1. Now I take 1 plus 2, I get 3. Now I take 2 plus 3, I get 5. Now I take 3 plus 5, I get 8, and so on. So basically it always grows, the step grows larger and larger. There is also a variant of this sequence where the first 2 values are 0 and 1. Basically the numbers are the same, but it starts with 0. But from there on the sequence is the same, just the first element is basically the elements are kind of shifted by 1 element. But yeah, mainly it's defined as so that the first 2 elements are 1 and 1. Let's see an example. So the Fibonacci example, recursive solution is something like that. So I have a function where I have this n, And if the n is smaller than 3, I return 1. So basically, if I call out the Fibonacci for 1 or 2, I get result as of 1, which is by definition correct. And now, basically, I could say that this is else, but I just don't write the else part because of this return, I don't need this else there. But you can think of it as it would be inside else branch. So now I return Fibo, the same function, but I call it out with n minus 1 and n minus 2 and add those two results up. And now if I see this, I run this example, Fibo 11, I get the result of 89. So what is Fibo 11? So I can say that, let's say this is Fibo 11. To calculate this, I actually need to know what's Fibo 10 plus Fibo 9. Now to calculate this one, I have to know what's the Fibonacci at position 9 plus Fibonacci at position 8. And for that, I have to know what's Fibonacci at 8 plus Fibonacci at 7, and so on. And to calculate this F9, again, I basically have to use the same here, and basically it grows with every step. And as you can see, to calculate this function or the 11th symbol or the 11th element, I have to do actually quite many callouts already for this function. And again, you can maybe see that although the 9th element is calculated here, I have to do it again here and so on. So there are a lot of repetitions in my code. So those are the same and so on. And to calculate the 11th element, I actually have to call out this Fibo function for 185 times. So to calculate 11th number, I have to do a lot of callouts. Now the same function, but I try to calculate what's the Fibonacci, what's the 14th Fibonacci element. And this is the example, the result here. This is something 102 million and so on. And to calculate that, it takes actually about 1 minute. And we did 200 million Fibonacci callouts during this calculation. And let's try to calculate Fibonacci for 1000. So what is the 1000th element in this sequence? But what happens is that we get an error. And the error says that the maximum recursion depth exceeded. And what it means is that we go into too deep with this recursive function. If I draw out the basically the calculation steps or procedure for this function call, I can say that every time I go deeper, F8 plus something, then there is F7 plus something, and F6 plus something, and so on, until we reach to F2, which for F2 we don't have to call out this function because this is the base case and we can return 1 right away. But basically it's the depth for this function. So if I call out the function with 1000, what it means is that for 1000 itself, it has to calculate Fibonacci's for 999, which means that it has to calculate the result for 998 and so on. So basically there are a lot of callouts. And to actually calculate this sum here, I have to know the result of this function and this function. And during my recursive function, I can do some additional, calculations and keep some variables in memory. So every callout here, the Python has to memorize it. So if I'm somewhere here, it has to memorize everything here, 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 and so on. So everything above this has to be memorized. So that's why we have a certain limit. This limit can be changed during the runtime. So if you really want to have a deeper kind of limit, you can change this limit. But anyway, at some point you will have this limit. For example, your memory gets exceeded or something like that. So, and by default, it's near 1,000. So let's look how the iterative solution would be. Here I have a function Fibiterative, which basically does the same. It calculates Fibonacci elements, but it does it with for loop. And here let's see what it does. So basically I have one variable fib and another priv, like previous. And first, both are 1. Now I go over, I do it n minus 2 times. N minus 2 because the 2 first steps are basically done here. And now the first thing I do is that the Fibonacci or the fib value would be fib itself plus previous. So basically to get the fib value I do 1 plus 1 and it's 2. And the priv value would be current fib, the new fib, minus priv. So basically I take 2 and take off 1, I get again 1. So basically it's 2 minus 1 is 1. Now I take the second step. Now I calculate fib plus priv. So basically to get this one I get 3 here. And here I take this minus current previous value is 3 minus 1 is 2. So basically the idea is that those 2 values represent the 2 last values. Here I have this 3 and 2. Now to calculate the next one is 5 and 5 minus 2 is 3. So basically we can say that this one goes here always. So the 5 goes here and the sum goes here. So 8 and 5 and so on. So I always have the 2 previous values. I don't need the rest. So basically to calculate this 11, I only have to know the 10th and the 9th element. But it's possible because I started from 0. In this example, it would be very hard to actually know what's the 10th value. But because I started from below, I already know what's the 9th and 10th value. Then I calculate the 11th value. I just sum those up. And now I can forget about the 9th element and so on. So that's the idea behind that solution. Of course, it can be written with more variables. You can basically have this third variable, which is the sum, and so on. Then maybe it's an easier, but this is one way to solve this. Having only 2 variables which represent the 2 last values. So to calculate this 11th value, it only is executed 9 times, this loop. It's less than it was for this recursive callouts where we had 180 something. And here I can see that I can calculate the 1000th element also. There's the result, and it's 209 digits, so it's a large number. I don't try to kind of name this value. And the iterative solution only takes 0.4 milliseconds. So that in comparison, where I had this recursive function, and to get the 40th number or element, it took me 1 minute. So here I take the 1000th element, and it only takes less than 1 millisecond. So it's less than 1,000th of a second. So it's at least 10,000 times faster. But then we can use tail recursion to write a recursive solution to this Fibonacci problem, which is also a bit more more efficient than the regular recursive solution. So here basically the solution is similar to this iterative function. We have this n is the number we want, or the number of the element we want to calculate. And this fib and priv are basically the same as here. We only want to keep the two last elements. And here what happens is that first the end condition is still the same here. If the n value is 1, then we just return this priv. Otherwise, we call out this same function. As you can see, instead of calling out two functions here, 1 and 2, now I only call 1. This already cuts down the callouts in my function. So basically, to calculate f11, I calculate f10. To calculate f10, I calculate f9, and so on. So basically, for 11, I have to do around 11 steps, 11 calculations. And here I pass on the two values, the first two values. And now for 40, I start with the call out for 39. Then I pass in the sum of those two numbers. So basically it's 2, and this fib is 1. And I'm going to subtract 1 in every step. So basically I start with 40 and I end up with 1. And the 1 is the goal here. So where I start, I end up with 1. This 1 actually doesn't mean the result. It's just a number of steps. We can think of it as that. So I start with 40, I end up with 1. So I have done 40 steps, because in every step I take 1 off of this 40 or whatever it is here. And what I return is this priv, this second or the third argument, or the third parameter. And here it is done that in every step this third argument gets the value where the current solution is held. So basically, first I pass in this sum here, but the sum is given into the second parameter, which is fib, and that's why the fib has always the sum of the previous two elements. But of course, it's if you want to kind of evaluate it yourself, it's always okay to kind of take this code and run the debugger with this code and see how it's done. So as you can see, to calculate this 14th element, it only takes 0.16 milliseconds. Versus this 1 minute I had with the regular recursive function or call out, where for every step I had to call this same function 2 times. But the problem is that this 1000 still gives me an error, although it probably is faster, but still there is a limit of callouts, and because it still goes from 1000 to 1, so it's still 1000 steps, it's still out of the limit for Python by default. But you can change that if you really want. So the tail recursion. So basically, the tail recursion is the one where the recursive callout is the statement, the last statement which is executed. So here I had basically also recursive functions, but the problem here is this plus. The plus is the last statement actually in this this line, because first it has to calculate the value of this, then it has to calculate the value of this, and the last statement or the last operation is this adding here, addition. In the previous example, the last callout was the call to the same function. So this is the last statement here. So there is no additional things to memorize. There is no additional things to consider or to calculate after the function call. So basically, after the function call to itself, there is nothing else to be done. And this actually allows optimizing the efficiency for this recursive callout. We can say that if this the recursion has this tail recursion variant, it is quite close to iterative solution, or it's actually depending on your I don't know, tools, you can say that it's basically the same. What can be done, the compiler can actually take this tail recursion and turn it into something similar as an iterative I don't know, solution. The thing is that it doesn't have to memorize all those states during this recursive callouts, and that's why it can be optimized. There is no requirement to store something in memory, because with that you have to take this memory, then you have to freeze this memory and so on. And also you don't have to do any additional steps for every recursive step. So, but in Python, in standard Python, it's not the case. So that means that in Python, you cannot use this tail recursion to optimize your code. And that's to do with how Python is implemented. There are actually packages which allow it. So if you install some additional package to your Python, you can use tail recursion and it's optimized. But otherwise in Python, if you use a recursive solution, it's always less effective or efficient than iterative solution. But still the difference might not be so bad. So if I compare this tail recursion with my iterative solution, the time wasn't so much off. It was maybe 10 times slower, maybe a bit more, but still the difference is not like a million times slower. But yeah, if you really want to achieve the same result as iterative solution, then you have to use some additional package in your Python. And this might change in the future. So maybe in Python, the tail recursion is optimized by default. But still, even though it's less effective or less efficient, there are still problems where it's wise to use. And often recursive solutions are simpler, or maybe not simpler, but they have less of line code. So basically lines of code. So you can say that it's simpler or easier to write. But that, of course, means that you have to understand the recursion. In the beginning, it might be very hard. But as you saw, there were one solution which only had 2 lines of code. So the condition for this base case and return or call out for the rest of the solution. So let's have a conclusion here. So the recursive function is the function which calls itself to solve a problem. And during this recursion step, a subtask is solved. So to calculate this Fibonacci, for example, I don't try to solve everything at once. I try to solve smaller problems. So I take 2 numbers and add them together. So basically this is the small step. I take 2 numbers and add them together. And now to get this first or the second part, I always also call out the same function, which is also adding up 2 numbers and so on. So basically I divide this huge problem into smaller problems and let the computer solve it for me. The recursive function always has to have a base case. So base case is the kind of condition where we have to terminate this call out, because otherwise, if I don't have this termination case or this base case, then the function calls itself out and it's never-ending loop. And all the recursive solutions can be written iteratively and vice versa. So if you have a standard problem or program where you have written your for loop, you can try to solve it recursively and vice versa. Of course, there are some problems where, for example, recursive solution has maybe 4 or 5 lines of code, but you turn it into iterative solution, you have to write, I don't know, 20 lines of code. So often recursive solutions are shorter. but not always. But still, you have to know that all the problems you can solve recursively, you can solve iteratively with for loops and vice versa.